Hello, I'm Dr. Ian McCullough from Johns Hopkins University. In this lecture, we're going to be talking about how you measure performance in an AI or machine learning algorithm. Now, this is based in statistical foundations, but I'm going to try and simplify all of the statistics with some simple examples. So let's look at the example of a loan threshold. So when you're a financial institution, what you ideally want to do is you want to give loans to people that will pay it back. You're going to have an interest rate. You make money off of loaning money to people that need it, and then you'll collect the interest rate and it makes money. But if you loan money to somebody that will not pay it back, then that's a much greater loss, right? And so let's say that there's two populations, and you can see here the darker dots will indicate people that will actually pay a loan back, and the lighter dots are people that will not pay a loan back. And we will create some sort of criteria that is represented along the x-axis. This could be credit score, this could be debt-to-income ratio, this could be age, right? There could be a whole lot of different factors that go into the decision to loan money. We're just going to simplify it and say there's one factor, let's call it credit score, and we're going to set an objective threshold, and anybody that has a higher credit score is going to get a loan, anybody that has a lower credit score will not. Now, when we set that threshold somewhere, right, if you look to the right, all the yellow dots are the ones that have been actually given a loan, and all the gray dots are the ones that haven't. You'll see that we did give a loan to those four light yellow dots that had the higher credit score but didn't pay the loan back. And you'll see to the left, there's some of those dark gray dots, which are people that would have paid the loan back, but we didn't loan the money. And so we can assess the performance of where this threshold falls, right? Or where this divider, this classifier of yes, no for loan award, where that goes. And so we can see that 87% of the dots, or 87, 88% of the dots are correct, in that we didn't give loans to those that wouldn't pay it back, the light gray dots, and we did give loans to those that would pay it back. Those are the dark yellow dots. And then we had 13% incorrect, which is 4 of the light yellow dots of people that we gave a loan to and didn't pay it back, or the dark gray dots are people we didn't give a loan to that would have paid it back, right? So we can assess the accuracy of this is about 87%. Well, let's go into other ways in which we can assess the performance of a model as simple as this one. So first of all, let us define positive and negative. So positive is going to be a successful payment, and negative is going to be somebody that would default on a loan, right? So what that means is we can have true positives, so that is indicating the 91 dark yellow dots that we gave a loan to, and we can have 4 false positives. So the positives are people that we're classifying as a successful payer, and so there's 4 of those classes are wrong, so that would be 4 false positives and 91 true positives. Similarly, we can identify true negatives. So those are those 95 light gray dots, and the 22 dark gray dots are people that we classified as negative and would default on the loan, but they would have paid it back. Okay? So with these 4 numbers, right, that you see visualized to your left, we can now calculate some more interesting metrics. So just looking at accuracy, the way we would define accuracy is the truth, right? The true positives and the true negatives in the numerator, and we would divide that by all of the potential classes that there are. And so you see that that ends up being 87.7%. Now, when we're talking about AI and machine learning, we tend to prefer to use other measures that are more descriptive and give us greater intuition on how the classifier or how the model is performing. So the first is precision, and precision is really saying when I say it's a good loan, it's a good loan, right? So how accurate are we at saying, yeah, this is a good loan? And so the way we define that is the true positives divided by the true positives and the false positives. So basically, we're just looking at the right side of the threshold there, and we're saying, how good are we at saying it's a good loan? And so in this case, we have 91 true positives over 91 plus 4 positives in general. And so that's a 95.8% precision. So that's telling us, hey, these are good loans. The other measure that's most common, second most common measure, is recall. And this is, do we grant all the good loans? How are we doing at making sure we give a loan to everyone that's qualified and will actually be a good bet and pay it back? So for recall, we look at the true positives and we are just looking at all the positive cases. So we're saying true positive divided by the true positives and the false negatives. So we're basically looking at how, of the dark bubbles there, or the dark circles of all the people who pay the loan back, how good were we at getting loans to all of those people? And so that's the true positive divided by true positive plus false negative, and we see we're at 80.5%. Now these are the two most common measures we use in AI, right? We want to say, hey, when we say it's the thing, is it the thing? And the other question is, hey, how good are we at finding all of the things? And so we typically, in most pilots, they will average these things together, and that is called the F1 score, which doesn't really have much of a meaning, but it's the harmonic mean of precision and recall. And what do I mean by harmonic mean? Well, instead of adding them together and dividing by 2, what we do is we multiply them together, and in doing so, what happens is if any one measure is really, really low, it gets multiplied, right? So if you have one measure at 0 and the other one's perfect, the overall score, 0 times 100, is going to be 0, right? It's going to cancel it out. So it is more sensitive to trade-offs in one or the other. Now, I want to just highlight a potential issue in AI and machine learning because a lot of times we start with pilots, and the pilots are done, and we evaluate the performance using precision, recall, and F1 score, and then we make decisions on how we're going to scale it. But there is a key issue with that. And what is that issue is disagreements. There's a point that I would like to highlight about training data that impacts performance, and that is that expert humans often disagree. Now, you're going to see case studies on all of these that'll go into more detail, but I just want to highlight it here. When we train AI algorithms, we're usually training them on labeled data. And the data is labeled by humans, and expert humans often disagree on what that label should be. Just to give you an example, when the post office was dealing with address resolution issues when they were mailing out COVID test kits, and we were trying to create a classifier to identify what the issue was, there was one of 5 different classes. The AI algorithm, the best at performing algorithm, was only about 83% accurate. So I asked postal workers to resolve some of these issues, right? About about 100 issues, and we found that their disagreement rate was 17%, meaning their agreement rate at 83% was about the same as the AI classifier's accuracy. Or with online extremism, this was a program I was doing for the U.S. Department of Defense to identify online extremist forums on the internet to counter propaganda. And they couldn't classify everything on the internet. They were trying. They were spending about $4 million a year in labor to try and classify whether it's pro-Al-Qaeda or pro-America, basically. And I decided to make a classifier that was 64% accurate, and everybody hated it because it sounded horrible. But when we paused and saw how often do people agree on the labels of what's pro-extremist, pro-Western, they disagreed 32% of the time. So you're really paying $4 million for a 4% marginal improvement while neglecting to address why 32% of the time you have an inconsistent label from humans. Most pressing, in the hypertension claim classifier for an AI system that would look at medical records and make disability claims estimations, our hypertension classifier was about 25% accurate. Well, one of our physicians noted that hypertension is often comorbid with other diseases like cardiovascular disease and diabetes and a number of other things. And so a lot of times it just doesn't get omitted or listed in the medical records because it's kind of implied. So when we had some physicians and nurses look back over the, about 1,000 medical records and say hypertension not, we were able to boost the data, the performance from 25% to 95% without ever touching the algorithm, just touching the data. And so what we find is when people disagree, when there's inconsistency in the labels, it adversely affects precision. But the volume of data improves recall. So if you have 4 annotators and one of them's not like the other 3, well, leaving their data in there to train an algorithm, right, is going to improve recall because you have more data, but it's really going to harm that precision. If you throw them out, you're going to get better precision, but you've lost data, so your recall will be affected. Now, what I would argue is in time, you're going to get more and more data in most systems, but if you don't do something to address like why people can't understand whether a website forum is pro-Al-Qaeda or pro-America, right, you need to address that early in the process so that you can identify and revise the standards so that you're labeling good, high-quality data going forward. Now, these aren't the only metrics that we use when we're looking at the performance of an AI algorithm. They're the most common ones. But let me just show you another one that is often used, and that is specificity. And so specificity is, do we deny all of the bad loans, right? Now, keep in mind, in a loan application sense, there's a greater cost to awarding a bad loan than there is to not awarding a good loan, right? There's a trade-off there. And so specificity is going to be looking at the true negatives. So we're looking at the true negatives and the false positives. So the true negatives, we're saying, hey, of all these bad loans, right, of all the light gray dots, so to speak, right, how many have we denied, right? So we're going to look at the true negatives divided by the true negatives plus false positives. In this case, we have 96%. So when we look at all of these measures, right, accuracy, precision, recall, F1, and specificity, which are probably the 5 most common ones, right, you can see that there is some trade-off, right, that goes from 88% accuracy, but it's high precision, low recall. You'll notice the F1 score is very similar to accuracy. You see that we also have high specificity in here, okay? Now, this is one model. So when we're looking at models, the simplest thing for a model is we can change some parameters in the model to try and make the model perform better. But what does that really look like? Well, if I take this loan situation and we have the same performance metrics I was just showing you, let's say I move the loan threshold a couple spots to the left in this example, right? I just move it to the left. How does that change these numbers? Well, I now have 101 true positives instead of the score in the 90s. I have more false positives. Instead of having 4, I'm now up to 10. I have, changed the true negatives, of course, and false negatives. And what this does is it leads to now, when I recalculate accuracy, precision, recall, F1, and specificity, it leads to a change in those scores. So we have more accuracy now by moving the threshold to the left. We have lower precision and lower specificity, but we have higher recall and higher F1 score. Now, it could be the case that the cost of awarding a loan to somebody who won't pay it back is more important than being able to get all of the loans to people that would pay it back. So I may be less interested in a more accurate model that has lower specificity and lower precision. Right? I may be less interested in that. And what I really want to do is go with the first model. Now, that is a decision that really is context specific, and it depends. And it's not always the financial bottom line that motivates people. A lot of times it's other things such as, equity. It's things such as, there's different risk profiles for each of these things that requires you to think through that in a little bit more detail. Now, the other thing that we often do is represent this with something called a receiver operating characteristic curve, or ROC curve. And so what we'll do is, in this example of where we're moving those thresholds, right? I showed you 2 thresholds, but we might have several different thresholds that we can do. And this is a discrete example, so it doesn't make as great of illustration. But when we look at the different levels, right? So I showed you the two extremes, A and C, and if we only did one unit to the left, that would be B. And what you can see in a receiver operating characteristic curve is we show the false positive rate along the x-axis, and that is kind of the inverse of specificity. So that's 1 minus specificity. So you'll see that lower model there with the colored green and red percentages, that's model C. And you can tell that because you'll see on the x-axis where it's 0.1 is 1 minus 90%, 0.9, right, is model C. And you'll see that the top model there with 96% specificity, well, 1 minus 96% would be 0.04. That would be model A. And then along the y-axis, we do true positive rate, which is the recall. So we're showing the recall percentage for those as well. And so what this does is it's showing you where A, B, and C fit along a trade-off, right, between these two values. Now, I'm not saying these are the two best values to use when you're looking at it. That's just what the receiver operating characteristic curve is using. And the other thing that will happen is if you take a different model, right? So we were using, something like, just a simple threshold model, but, you can imagine a more advanced, AI model where you're comparing, well, what if I use a random forest or a neural network or a naive Bayes, right? And then what are these curves looking like between these trade-offs, right? Well, when we represent that, one of the measures we can use on our receiver operating characteristic is the area under the curve. And so the area under the curve would actually basically be the lower right. Now, a really good curve would be one that if that threshold B was way up here in the upper left corner where the legend is, right? So you have more of a highly tuned thing where you can clearly pick something that's going to have both high precision and high specificity, right? High recall and high specificity. That would be considered a better model than one that is more of a smooth trade-off. And so what these lines let us do is they let us compare different models. And so one of the simple metrics we use is area under the curve, which is all that area to the lower right. So when the area under the curve is higher, it means that the model is doing a better job at having high compromise between specificity and recall. So this has been a short lecture on performance measures in AI and machine learning.